Okay, so welcome everybody, and a great welcome for Professor Chang today. It's a great honor to have you with us. And Professor Chang is Henry Kenner Early Career Professor in the Department of Physics of Pennsylvania State University. And Prof. Chang received his PhD in physics in 2013 from Tsinghua University in China. So before he joined Penn State, he did 4 years postdoctoral work at MIT. And Prof. Chang is a world-leading expert in molecular beam epitaxy group of quantum material, particularly the quantum anomalous Hall, so QAH in short, insulator. And Prof. Chang was the first to realize the QAH effects using a magnetically doped Topological Insulator thin film in 2013. So this work was done in China or in MIT?
No. Today, most of the work in my talk today is the recent work done at Penn State.
I was talking about the first QAH.
That's in Tsinghua, in China.
That's in Tsinghua. Okay, I see. So his recent interests include the pursuit of high temperature and high Chern number QAH insulator, and the exploration of Majorana physics in this QAH superconductor hybrid structure. So he's very young but very talented researcher, and he has many awards, which include the Rustum and Delta Roy Innovation in Material Research Award in 2021, the Gordon and Betty Moore EPIQS Material Synthesis Investigator Award in 2019, the Mark Konix Prize, so it's an outstanding Chinese young researcher award, the same years, the NSF Career Award also in 2019, the RAO Young Investigator Program Award in 2018, the Alfred Sloan Research Fellowship in 2018, and the IUPAP Young Researchers Prize in 2016. So that's a lot of things for very short career. And I have to say also that, I mean, Prof. Chang is very productive researcher. He has more than 100 papers right now, including, of course, many prestigious review. So thank you very much to be with us, and the floor is yours.
Okay, thank David for the kind introduction. My name is Cui-Zu Chang from Penn State. Very happy to give a talk at the Nanyang Tech University. Actually, this is the second time for me to give a talk at NTU. I visit and give a talk at NTU in 2015. When I attended a meeting in Singapore, so the 6 years ago. So also in physics department. So the title of my talk today is Quantum Anomalous Hall Effect in the Magnetic Topological Insulator Multilayers. So let's start with dissipation-free phenomena in kinetic matter physics. That this is a Colloquium talk, so I started with very simple phenomena. So we know that there are only two phenomena in the kinetic matter physics showing the zero resistance. The first one is well-known superconductivity. So it was first discovered by the hacker Anomalous in the 1911. And the second dissipation phenomena is the quantum Hall effect. It was first discovered by the German physicist von Cauchy in the 1980s. And we note that in the quantum Hall effect, the bulk is an insulator, and the dissipation current flow through the edge of the sample like this. So the quantum Hall effect can only be realized in high mobility two-dimensional electron gas and a very high magnetic field. Today in my talk, I will talk about a unique quantum Hall effect under zero magnetic field. We name it quantum anomalous Hall effect. In the last several slides of my talk, I will discuss the Majorana physics. by combining these two phenomena, superconductivity and quantum anomalous Hall effect. So first, I want to acknowledge my postdoc, my students, and also my collaborators. I really appreciate their help and support. And the research in my group is supported by the federal agency and also some private foundations. So here is the outline of my talk. I will first give a brief introduction about this kind of the quantum anomalous Hall effect and topological insulator. I will show you why and how we use the topological insulator to realize the quantum anomalous Hall effect. You may know that with many efforts in 2013, as David just introduced, we were the first to realize the quantum anomalous Hall effect in the chromium-doped topological insulator thin film when I was a graduate student in Professor Cui-Zu's group at Tsinghua University of China. So after 4 years, the postdoc at MIT in 2017, I joined the Penn State. The first project we are doing is that we just fabricate this kind of the magnetic TI symmetry structures. And we realized one phenomenon called the axion insulator state. And we also fabricate the magnetic TI and TI multilayer structures and realize the high chain number quantum anomalous Hall effect in magnetic TI and TI multilayers. And based on this kind of the quantum anomalous Hall insulators, we fabricated the quantum anomalous Hall and the superconductor hybrid device, and found that the actually is a pretty negative result. Is the found that the observation of the half quantized plateau in transport is unlikely induced by the formation of the chiral Moranas. Our work should be the first condensed matter negative papers published in Science in the 2 years ago almost. So finally, I will give a brief summary. So let me introduce the Hall effect. The Hall effect is a very famous phenomenon in condensed matter physics. When the current flows through a conducting material, which is in a perpendicular magnetic field, the charge carrier will be pushed towards the side of the sample by the Lorentz force, and a transverse voltage called the Hall voltage will develop across this sample. This effect, we usually call it Hall effect. And the Hall effect was first discovered by the Edwin Hall in 1879. At that time, he was a graduate student at Johns Hopkins University. This is the Edwin Hall's original data on a good leaf. The Hall effect is still being used to identify the carrier type and the carrier density and the carrier mobilities of the samples in the condensed matter physics field. So in this kind of the Hall effect, we will ask what will happen for the Hall effect if we further increase the magnetic field. You see here, the magnetic field is 1 Tesla. If we further increase the magnetic field, what will happen for this kind of Hall effect? And most electron will be pushed towards the two sides of the sample and make the bulk become insulated. This is just the quantum Hall effect. This is a very simple pictures to understand how we could convert this kind of the Hall effect to the quantized version. The quantum Hall effect was first realized, as I just introduced, in 1980s by von Cleansing. In this kind of the quantum Hall effect, this is the 2D electron gas in the silicon oxide, this kind of the device. And in the quantum Hall effect, we can see at high magnetic field, the Hall resistance is quantized and the longitudinal resistance become 0. As I just said, the Hall effect is usually observed in two-dimensional electron gas system under very high magnetic field. The quantum anomalous Hall effect today, in my talk, I will focus on the quantum, a special kind of the quantum Hall effect. We call it quantum anomalous Hall effect. Quantum anomalous Hall effect is just the zero magnetic field quantum Hall effect. You know, this is the so-called the Hall family. You know, there are three basic members: Hall effect, anomalous Hall effect, spin Hall effect, and their quantized version: quantum Hall effect, quantum anomalous Hall effect, and quantum spin Hall effect. You know, quantum spin Hall effect is just the two-dimensional topological insulator. So today in my talk, I will focus on the general belief that the last member of the Hall family is quantum anomalous Hall effect. You know, in quantum anomalous Hall effect at zero magnetic field, you know, the anomalous Hall resistance is quantized. And at the same time, the longitudinal resistance becomes zero. And we can see that in this kind of the quantum anomalous Hall insulator at zero magnetic field, when the magnetization up, the chiral edge state goes this way. When the magnetization is down, the chiral edge state goes the opposite way. So the chirality of this kind of edge state depends on the magnetization direction of the sample. You know, this kind of edge state, we usually call it spin-polarized ballistic chiral edge state. So before moving on, let me see a few words about this kind of the chiral edge state in the quantum anomalous Hall insulators. You know that in a toy model for the conventional conducting materials, there are 4 degrees of freedom. You know, spin up, spin down, right mirror, and left mirror. You know, the impurities in this kind of the samples can backscatter the right mirror to the left mirror. So this can give rise the electrical resistance in the conventional conductors. But in the quantum anomalous Hall insulators, there is only 1 degree of freedom, means the spin polarized edge channels. This kind of edge channels is called the chiral edge state. You know, the electrons in this kind of conventional conductors looks like the bus and the cars in a traffic jam. And the electrons in this kind of the quantum anomalous Hall insulators, just like the traffic on the highway. So the edge state of the quantum anomalous Hall insulators actually give us a platform for the next generations of energy efficient the electronics and spintronics with low power consumptions and also topological quantum computings. So unlike the quantum Hall effect, you know, we know the quantum Hall effect, which starts from the experiment and later theorists try to explain it. But for quantum anomalous Hall effect, actually was first predicted by Duncan Haldane in the 1988, you know, just because of the prediction of the quantum anomalous Hall effect. And Haldane received the Nobel Physics Prize in 2016. And the Haldane's model was based on this kind of the 1 layer of the carbon atom. You know, now today we usually call it graphene, you know, in this kind of the periodic magnetic field, but without net flux. You know, Haldane took the nearest neighbor hopping and the second nearest neighbor hopping in his calculation. You know, if the second nearest neighbor hopping T2 here, T2 is 0, you know, there will be 2 Dirac coins at the corners of the Brillouin zones. You know, this is just a graphene. We know that the Dirac coin is located at the gamma point of the graphene. And when the phase phi of the second nearest neighbor hopping is included in his calculation, the time reversal symmetry of the system will be broken and a gap will be open at the Dirac point. You know, according to the Haldane's theoretical prediction, if we could tune the chemical potential into this small gap, we could realize the quantum Hall effect under zero magnetic field. In other words, it's quantum anomalous Hall effect. So, but in reality, we know that due to the very weak spin-orbit coupling, we could not realize quantum anomalous Hall effect in the graphene system by the magnetic doping because the SOC is too weak in the graphene system. And on the other hand, the quantum anomalous Hall effect can also be considered as the quantized version of the anomalous Hall effect. And the anomalous Hall effect is the Hall effect in the ferromagnetic materials. And the anomalous Hall effect in the ferromagnetic material can be intrinsic and extrinsic. You know, today in my talk, we will focus only on the intrinsic anomalous Hall effect. The intrinsic property of the anomalous Hall effect was first recognized by the Kempler's and Latinger. You know, they thought this kind of the intrinsic anomalous Hall effect was induced by the property of the energy band rather than this kind of the impurities in the sample. You know, when the barrier language was developed in the 1980s, the Hall conductance can be calculated by this kind of the integral of the barrier curvatures in the first Brillouin zone. The integral of the barrier curvature can be calculated, can be written by 2 pi times c. C is just we call it chain numbers. It's just how many this kind of chiral edge state in the quantum anomalous Hall insulators. We will talk more later. And from these two equations, we can get a very simple equations. You know, sigma s squared equals E squared over H times C. C is the chain number. You know, from this equation, we can get the two conditions for the realization of the quantum anomalous Hall effect. You know, if C is non-zero, this one can be quantized. You know, C is non-zero, just the material is inverted band structure. You know, today we usually call it topological material. You know, the material is topological material, means C is there, and C is non-zero. And at the same time, it should be there is anomalous Hall effect. So this should be ferromagnetic insulators. You know, if one material satisfies these two conditions, we could realize the quantum anomalous Hall effect. But we know that in the reality, it's very difficult to find this kind of the materials with these two properties. And in 2006, you know, the discovery of the topological insulator, you know, topological insulator made the search for the quantum anomalous Hall effect become possible. So let me introduce the topological insulator is. You know, this is a band insulator. This is conduction band, and this is valence band. You know, when the strong spin orbit coupling is introduced in this kind of the band insulator, the conduction band and the valence band will become inverted, and a linear dispersion, this kind of the surface state, will be formed between the conduction band and the valence band. We can say that this is just the topological insulator. You know, obviously, the topological insulator satisfies the first condition with the inverted band structures in the sample. And let me see a few words about topological insulator before we move to the quantum anomalous Hall effect. You know, the topological insulator can be clarified into 2D topological insulator and also 3D topological insulator. You know, both 2D and 3D topological insulator has been realized in the real materials. And the 2D topological insulator was first discovered in the mercury telluride quantum wells. You know, 2D topological insulator is also called the quantum spin Hall insulator. And later in this kind of the indium arsenide and gallium antimony quantum wells, and more recently in the monolayer 1T primer tungsten telluride. And the 3D topological insulator was first discovered in the bismuth antimony compound, and later in this kind of the bismuth selenide family materials, and later there are lot of materials discovered for this kind of the 3D topological insulator. You know, in my experiment, we focus on this kind of the bismuth selenide family materials for the realization of the quantum anomalous Hall effect. You know, as I just showed you, the topological insulator already satisfied the first conditions for the realization of the quantum anomalous Hall effect. You know, this is topological insulator. There is inverted band structure and forms this kind of the Dirac surface state. And this Dirac surface state is protected by the time reversal symmetry. So the second condition is how to introduce the ferromagnetic orders in the topological insulator. You know, that's the, if we introduce the ferromagnetic orders in this topological insulator, the time reversal symmetry of the topological insulator will be broken, and a gap will open at the Dirac point. You know, this gap, we usually call it magnetic exchange gap. If we tune the chemical potential into this small gap, we could realize the quantum anomalous Hall effect. You know, this is just the a very simple pictures to understand why we choose the topological insulator for the realization of the quantum anomalous Hall effect, and how to use the topological insulator to realize the quantum anomalous Hall insulators. You know, that is just a theoretical picture. As an experimentalist, we need to convert the theoretical picture into some experimental step and procedures in our experiment. You know, there are 3 steps, and the first step is we need the high quality topological insulator thin film. You know, our approach is just MBE growth. I'm an MBE brewer. And the second is we need to introduce the ferromagnetic properties into topological insulator thin film. You know, we realize just we're using the approach in the diluted magnetic semiconductor. We're using the magnetic doping effect in this topological insulator to realize ferromagnetic order. And the third condition is just we need to tune the chemical potential into this small gap. You know, we need to tune the chemical potential to the insulating regime. We're using the 2 methods. One is the chemical doping, and the other is the gating effect. And next, I will briefly show you how to reach the quantum anomalous Hall step by step when I was a graduate student. You know, here we're using the MBE to grow the 3D topological insulator. By very carefully control the growth parameters, we were able to achieve the layer by layer growth of the bismuth selenide thin film. And this is the bismuth selenide film grew on the graphene substrate. And we performed the RPS measurement. We can see this 1 quintuple layer to 6 quintuple layer. And when the film is above the 6 quintuple layer, there is a Jacob surface state formed. And in all these film, we can see there is very well-defined quantum well states. That indicates our MBE grew in this kind of the TF film is uniform. And we can also see a gap opening between this kind of the 2 quintuple layer and 5 quintuple layer. That's just because of the top surface state and bottom surface state, the hybridization effect to induce this gap opening. You know, this is the first step. And the second step is we need to introduce the ferromagnetic orders. You know, as you may know, there are 3 members in bismuth selenide family topological insulators: bismuth selenide, bismuth telluride, and antimer telluride. You know, we tried very hard and all the transition metal in the periodic table and found the chromium is the best candidate. So we doped chromium in these 3 topological insulator, and in chromium doped bismuth selenide, there is no hysteresis. It's just a nonlinear behavior. So this is not long orders ferromagnetic property. It's just a paramagnetism. So we forget this kind of the chromium doped bismuth selenide as a candidate for the realization of the quantum anomalous Hall effect. So the good news here is chromium doped bismuth telluride and chromium doped antimer telluride, both of them are ferromagnetic. And at low temperature, it shows the ferromagnetic hysteresis. And there is another good news here is this one is N-doped and this one is P-doped. As I just showed you, the third step for the realization of the quantum anomalous Hall effect, we need to reduce the carrier density to make it in the insulating regime. So here, we choose these 2 material as the candidate for the realization of the quantum anomalous Hall effect. And the very straightforward direction is we combine them together, we mix them together to grow the chromium doped bismuth antimony tellurium film. This is the reason why we choose the 4 element topological insulators for the realization of the quantum anomalous Hall effect. So here, let's say the transport results. You know, we need to tune the bismuth antimer ratio to make it become an insulator. You know, if the sample is a good insulator, in principle, according to the theoretical prediction, we could realize the quantum anomalous Hall effect. So here is 5 quintuple layer chromium doped bismuth antimony telluride, and we can see that we systematically change the X, the bismuth doping level. This is pure chromium doped antimer telluride, and 15%, 20% to the half of the bismuth dopings in the sample. We can see that from this data, we can see that when you change the bismuth doping level, the ferromagnetic material can become this kind of the p-doped to the n-doped. So from p-doped to the n-doped, there definitely some point we could realize the insulating ferromagnetic topological insulators. And we can say that when you tune the carrier density and the carrier type, the ferromagnetic property is always there. It's not looks like the diluted magnetic semiconductor. The ferromagnetic property can only be realized in the p-doped regime. So here actually tells us the ferromagnetic property can survive in the insulating regime. This is a good news for the quantum anomalous Hall effect. And we can see the anomalous Hall resistance actually increase in the insulating regime. Here is just a 3 kilo ohm. Is still far from the quantized value. You know, our goal is the H over E squares Hall resistance is 25.8 kilo ohms for the Hall resistance. And so with the, you know, next we just optimize the growth condition and we change the thickness of the sample, change the bismuth-antimer ratio, and change this kind of the geometries for the Hall environment. And with many efforts, in 2013, we were the first to observe the quantum anomalous Hall effect in the 5 quintuple layer chromium-doped bismuth antimony tellurium telluride film. Here, we can see that this is the magnetic field dependence of Hall resistance and longitudinal resistance. We can see that at 0 magnetic field, the Hall resistance is quantized and the longitudinal resistance is close to 0. And if we plot the 0 magnetic field, just here, the Hall resistance and longitudinal resistance as a function of the gate, we can see that at the charge neutral point, the Hall resistance is quantized and the longitudinal resistance shows a sub dip here. You know this, and here is the, it's not still not 0, it's 2.5 kilo ohm. It's not completely dispensionless transport, but this kind of the deep feature, you know, this kind of the observation here marks the first discovery of this kind of the quantum anomalous Hall state in the magnetic doped topological insulator system. And when I graduated from the Tsinghua University, I moved to MIT for my postdoc, and I realized this kind of the high precision quantum anomalous Hall state in the second system just changed the magnetic doping, changed the chromium doping to the vanadium doping. Actually, the reason I didn't using the vanadium when I was a graduate student is just the DFT calculation said vanadium is not good. But when I was doing the experiment, I found the vanadium doped TI actually shows the best ferromagnetic property. So that's the reason we choose this one. And finally, we realized the very good, very high precision, this kind of the quantum anomalous Hall state in the vanadium doped topological insulator system. And in this system, at 0 magnetic field, the Hall resistance is fully quantized and the longitudinal resistance is only less than 3 ohm. And we also performed this kind of the local and non-local environment and perfectly demonstrated the chiral eddy transport in the quantum anomalous Hall insulators. And after 4 years postdoc in MIT in 2017, I joined the Penn State, and the first project is the realization of the axion insulator state in the magnetic TI symmetry heterostructures. You know, axion is definitions from the particle physics, which is hypothesized by the Frank Wilczek and as yet observed in this kind of the particle physics field. And to realize the axion insulator state in the topological materials, we need to satisfy these 3 conditions. The material need to be in the 3D TI regime, and all surface should be gapped, like a ball, all surface gapped, and the bulk maintains the time reversal symmetry. But the bulk is still the inside of the ball is still keeps the time reversal symmetry. So as I just introduced, and we already realized the quantum anomalous Hall in the chromium doped TI and also vanadium doped TI. And these 2 systems have different coercivity field. And vanadium doped TI, the coercivity field is almost 1 Tesla here, and the chromium doped TI the coercivity field is only 0.15 Tesla. So we were thinking to grow this kind of the sandwich structures. The bottom layer is chromium doped Ti, and the middle layer is n-doped Ti, and top layer is vanadium doped Ti. When at a very high magnetic field, they will align to the same direction. This is just the quantum anomalous Hall state. At some magnetic field regime, maybe the chromium doped Ti points down and vanadium doped Ti points up. So, in this kind of the situation, this is gapped, and the side surface, there is no chiral eddy state, and because of the quantum confinement effect, there is also gap opening. All the surface are gapped, and in the middle maintains the time reversal symmetry. This just satisfies all three conditions of the axion insulator state. So this is the sample we grew in our experiment. We grew 3 quintuple layer chromium doped Ti, and also 3 quintuple layer vanadium doped Ti on the top, and in the middle we changed the different thickness. And this is the TM of our sample. It shows the pretty good quality of the magnetic Ti sandwich structure here. Let's take a look at the transport result. We noticed that in quantum anomalous Hall effect, why we could observe the E square, H over E square, this kind of Hall resistance, and E square over H, the Hall conductance. The reason is each surface contributes E square over 2H Hall conductance. Two surfaces will contribute E square over H Hall conductance. If in this kind of situation, the top surface is E square over 2H, the bottom surface is minus E square over 2H. The total Hall conductance becomes 0. This is the Hall result. We can say that at very high magnetic field, this is the quantum anomalous Hall state. When you sweep back the magnetic field, the chromium doped layer, because the HC is smaller, the chromium doped layer will flip first and forms this kind of the anti-parallel alignment. This is the Hall conductance become 0. And if you further sweep, the vanadium doped layer will also point down. This is quantum anomalous Hall again. And when you sweep back, it reproduces, repeat this kind of the behaviors in this kind of the transport environment. This is just the axion insulator state, the 0 Hall conductance plateau in the Hall conductance environment. And for this kind of the realization of the axion insulator state is a good platform for the detection of one phenomena, is we call it topological magnetoelectrical effect. We notice the magnetoelectrical effect. In this kind of material, there is a topological magnetoelectric. We also call it TME effect. In TME effect there are 2 signatures. One is the M, and E is the induced E, and the applied magnetic field. They always parallel with each other. And at the same time, the coefficient between them is also quantized. This kind of experiment is still undergoing in my group. And in addition to the quantum anomalous Hall effect in the chromium doped and vanadium doped Ti system, once the first system realized in 2013, and later in 2015, we realized vanadium doped quantum anomalous Hall system. And more recently, just in 2020, and also this year, there are 3 systems also realizing this kind of the C equals 1 quantum anomalous Hall effect. We can say is the first system is the exfoliate, that's the 2D materials. Exfoliate manganese bismuth telluride is intrinsic magnetic Ti on 1 to 4 phase. With the older number layers, we could realize the quantum anomalous Hall. And in this kind of the twist bilayer graphene system, this is not the magnetic doping approach. And here is we could also realize the quantum anomalous Hall effect. And just more recently, in the AB stacked multitelluride and tungsten selenide bilayer structures, also quantum anomalous Hall effect realized. And we see that in all these systems, including the chromium and vanadium doped Ti system, the chain number is always 1, is the E square over H here, E square over H, and this is 25.8 kilo ohm. And in this kind of quantum anomalous Hall insulator, the chain number is 1. We notice that in quantum anomalous Hall, we always say, as I just introduced, there is this pinching chiral eddy state. but the contact resistance is still huge. It's H over CE squares. And if you know if we want to before moving on, let's compare the C equals 1 quantum anomalous Hall effect and the high chain number quantum anomalous Hall effect. You know, if we want to reduce the contact resistance, we need to increase C here. You know, let's say this is the C equals 1 quantum anomalous Hall effect. In C equals 1 quantum, there is only one chiral eddy channels. You know, when the electron is traveling in this kind of chiral eddy channels, just like the cars from the highway to the downtowns, you know, it usually takes a lot of time. However, in this kind of the high chain number quantum anomalous Hall insulators, there are several this kind of the chiral eddy channels. It will greatly reduce the time from the highway to the downtown of the city. So, you know, the more recently we realized the high chain number quantum anomalous Hall insulators by stacking this kind of the C equals 1 quantum anomalous Hall layer and the normal insulator layers forms this kind of the multi-layer structure. You know, this is the C equals 3 quantum anomalous Hall insulator. This is just the momentum space, the chiral eddy channels under different these kind of the magnetizations. And you know, just from the MBE group's point of view, it's very difficult to find this kind of the normal insulators layers. You know, we need to make this kind of normal insulator share the same lattice structure with the quantum anomalous Hall layers. So in our experiment, actually the idea is like this. You know, we heavily doped chromium in this kind of the magnetic tier layers. You know, the heavily chromium doping can reduce the spin-orbit coupling because chromium is much lighter than the bismuth or antimony in the topological insulator films. You know, if we dope very much chromium, we could reduce this kind of spin-orbit coupling and drive it to the normal insulator regime. And in this kind of the undoped tier layer regime, we could realize the C equals 1 quantum anomalous Hall layers. And therefore, you know, this is we grew this kind of the very heavily doped chromium doped TI and pure undoped TI in this kind of the multi-layer structures. And this is the TM image. We could see the very highly ordered lattice structure here. And we fabricate the magnetic TI multi-layers with the 1 period, 2 period, and to 5 period. We performed the transport measurement. We see that here the Hall resistance is quantized at H over E square, and in here is H over 2E square and H over 3E square to the H over 5E square. In all these samples, we can see that the longitudinal resistance is vanishing at 0 magnetic field. And this kind of observation indicates the realization of the quantum anomalous Hall insulators with the chain numbers from 1 to 5. And the chain numbers of the quantum anomalous Hall insulator is determined by how many these kind of the layers of the undoped TI layers in this kind of the multi-layer structure. For example, if there are 2 undoped TI layers, the chain number will become 2. And the high chain number quantum anomalous Hall insulators are further demonstrated by the gate dependence of the ferromagnetic field Hall resistance and longitudinal resistance. We can see this is quantized at H over E square to the H over 5E square. At the charge neutral point, the longitudinal resistance is vanishing in all these samples. You know, this kind of the gate dependence data, you know, clearly demonstrated the realization of the high chain number quantum anomalous Hall insulators with chain numbers from 1 to 5 in this kind of the multi-layer structures. And in the same sample structure, we actually found that the chain number can actually be tuned by changing the magnetic doping concentration. You know, let's take this kind of the pentalayer structure, these 5-layer structures as an example. You know, we found that in this kind of this magnetic TI and this undoped TI, we found that with the lower doping level, the chain number is 1. With the higher doping level, the chain number becomes 2. You know, for the lower doping level, we know that as I just show you, the lower doping level, the spin-orbit coupling is still strong enough to make this kind of the magnetic tier layers in the non-trivial regime. And at the higher magnetic doping level, this magnetic tier will become the trivial. So there will be two quantum anomalous hole here. It's just a series connection here. That's the reason we could realize the C equals 2 quantum anomalous hole insulators here. And this kind of the chain number tuning is further demonstrated by this kind of the gate dependence of the zero magnetic field Hall resistance. We can say that with the lower doping level quantized at h over e square, at higher doping level quantized at h over 2e square. You know, our experimental result is well interpreted by our theoretical calculation by my colleague, Professor Chang in our department. So in addition to the magnetic doping level, we also tune the Chern numbers just to tune this kind of the thickness. You know, tune the thickness just to tune the interactions between this kind of the quantum anomalous hole layer, and tune the thickness here. And we found that when D equals 0 and 1 quintuple layer is C equals 1 quantum anomalous hole insulators. When the D is from 2 to 4 is C equals to 2 quantum anomalous hole insulators. You know, we notice that when the middle layer is very thin, you know, the top quantum anomalous hole and the top and bottom quantum anomalous hole shares the same topology. You know, they will become one quantum anomalous hole. That's the reason we realize the C equals 1 quantum anomalous hole insulators. And when the middle layer is very thick, the interaction is not enough. So that's the reason there are two separate quantum anomalous hole insulator layers here. You know, that's the reason we could realize the C equal to 2 quantum anomalous hole insulators here. And the chain number tuning by this kind of the thickness of the middle magnetic tier layer is also demonstrated by the gate dependence result. We can say that this is the 1 quintuple layer and 0 quintuple layer is quantized at h over e square, and from 2 quintuple layer to 4 quintuple layer quantized at h over 2e square. This is the C equal to 2 quantum anomalous hole. This is C equal to 1 quantum anomalous hole. You know, this kind of experimental result is also interpreted by our calculation. And finally, I will introduce, in the last several slides, I will introduce our work about the Majorana physics in the quantum anomalous hole and the superconductor hybrid structure. As I just told you, quantum anomalous hole and superconductivity, and these are two phenomena in the condensed matter physics showing the zero resistance. And in this kind of the quantum anomalous hole, this is quantum anomalous hole, and this is superconductor. You know, there is the chiral Majorana formed in this kind of heterostructures. So here there are 4 chiral Majoranas, is gamma 1, gamma 2, gamma 3, and gamma 4. So there are 4 chiral Majoranas. So this kind of the chiral Majoranas can be detected by this kind of the transport configuration. You know, this is a very simple configuration. And the only thing we need to do is just put a superconductor layers on top of the quantum anomalous hole layers. You know, there will be 4 chiral Majorana forms in this kind of the crossed quantum anomalous hole and the superconductor hybrid structure. You know, based on the theoretical prediction, based on the theoretical prediction, the expected transport data are here. You know, this is just a theoretical prediction. We can see that the top is just the Hall conductance. You know, this is the quantized E square over H, this quantum anomalous hole, this quantum anomalous hole. There is 0 Hall conductance plateau here. And the bottom, the below is just the 2 terminal conductance. You just measure the electrode 1 and the contact 2. You measure the 2 terminal resistance. If you see this kind of the transport behavior and this kind of the half quantized plateau here, we can see there are 4 half quantized plateau here. When you sweep the magnetic field, this half quantized plateau indicates the formation of the chiral Majoranas. Before moving on, I want to point out in this theoretical prediction, the superconductor was just considered as an insulator with a very small gap. But we know that at least for experimentalist, we know that in real experiment, a superconductor is not an insulator. So, and soon after the theoretical prediction, an experiment come out from the UCLA group and claimed the observation of the chiral Maranas in the quantum anomalous hole and nanobeam device. Let's compare the experimental result. This is experimental results, and this is the theoretical prediction. It's just this one. And let's compare these two results. We can see that here is just the t equals 2. Here let's define a superconducting chain number. It's just the chain number I defined previously. The 2 times the chain numbers is we call it n. And here is just the n equals 2 regime. Here is n equal 2 regime. And here is the n equals 0 regime. When you tune the magnetic field, it will definitely pass through the n equals 1 regime. This is just the chiral Marana. Why this kind of half quantized plateau and indicates the formation of the chiral Maranas in this kind of the quantum anomalous hole and superconductor hybrid device. But I want to see that we can see that this is experimental results and this is the theoretical results. They look remarkably similar. And we will ask is this kind of the half quantized plateau here, half quantized plateau is really induced by this kind of the formation of the chiral Maranas. So that we also did this experiment in 2009, and this is our device, and this device includes 2 parts, and this part is actually quite similar as this kind of parts, and we put a nanobeam strip here, and this is a hole bar, and we could measure the 2-terminal resistance to check the 2-terminal resistance shows this kind of half quantized plateau or not, and to see if that kind of half quantized plateau is indeed related to the chiral Marana. And this side, we call it quantum anomalous hole nanobeam finger device. We put a very narrow this kind of the nanobeam here. We want to do the anomalous reflection measurement to check the transparency between the quantum anomalous hole and the superconductor layers. And we performed the anomalous reflection measurement and confirmed the transparency between quantum anomalous hole and superconductor nanobeam is very good in this kind of the device. And we performed the 2-terminal measurement and performed we measured the resistance between the contact 1 and contact 2. This is our result. Our result is completely different from the one shown here. And we can see that in all this regime, it shows the E square over 2H half quantized in this kind of the well-defined regime. Only in this kind of the 2HC regime, it is not E square over 2H. We will ask this kind of the E square over 2H observed in our experiment is indeed related to chiral Marana or not. So we did this kind of the control measurement. This is actually a very simple control measurement. This is the structure I just introduced you. If you put a superconductor layer here, this forms the TSC regime, topological superconductivity regime. And if you take the measurement between contact 1 and contact 2, if you see the E square over 2H plateau, it may related to this kind of the chiral Marana. But if we put 2 superconductor strip here, according to the theoretical prediction, it will form 5 Marana here. It gamma 1 to gamma 5. When you take the measurement between the contact 1 and contact 2, it should be still E square over 2H. If you put 2 of them, it's E square over 2H. That means when you observe the E square over 2H in this kind of the one strip structures, it may related to the chiral Maranas. So we did this kind of the measurement. Here are the transport result. When one strip we put here, the 2-terminal resistance is E square over 2H. When 2 nanobeam strip here, we can see that the 2-terminal resistance becomes E square over 3H rather than E square over 2H. As I just introduced here, if this kind of the 2-terminal resistance related to the Marana physics, it should be constantly E square over 2H. But in our experiment, it becomes E square over 3H. Therefore, we conclude that the two terminal resistance here observed in this kind of structure is just a series connections series connection of the two quantum anomalous Hall sessions. You know, this side is a quantum anomalous Hall, a two terminal resistance E square over H. This side is E square over H. This is just a normal contact here. It's just a series connection. It's E square over 2H. You know, we have measured 30 samples at Penn State, and similar results has been observed in the Lawrence-Mollenkamp's group in Germany, and also David Gold-Hartmann's group in Stanford, and also my PhD supervisor's group, Cui-Zu's group in Tsinghua. And here we come to an end with the summary. You know, we are the first to realize the quantum anomalous Hall effect in the chromium and also vanadium doped film. And we fabricate the magnetic TI semi-structure, and we observe the axion insulator state for the first time. And we fabricated the magnetic TI and TI multilayer structures, and we realized the high chain number quantum anomalous Hall insulators. And by tuning the chromium doping level and the thickness of the middle magnetic TI layers, we could tune the chain numbers in the quantum anomalous Hall insulator layers. And based on this kind of the quantum anomalous Hall insulators, we fabricated the quantum anomalous Hall and the superconductor hybrid device. We found that the half quantized plateau in transport is unlikely induced by the formation of the chiral-Marana excitations. With that, thank you.
Thank you very much for this very, very nice talks. I mean, thank you for the general introduction. And I think we already have a question from Weibo. Yes, please, Weibo.
Yeah, thank you for the very nice talk. So then this is a good result to see that this is just a series of resistance, right? Is it resistors instead of the chiral-Marana physics. So then is there one way to build this kind of chiral-Marana devices? Any other approach in your mind? This is one question.
Yes, let me answer this question first. So I think the Marana physics in the quantum anomalous Hall and the superconductor heterostructure is definitely, you know, quite simple. I think the theory should be correct. So, but I don't think this kind of the geometry to demonstrate it for the demonstration of the Marana physics in this kind of the geometry is good. In my opinion, if we want to confirm the Marana physics in quantum anomalous Hall superconductor or topological insulator superconductor, this kind of hybrid device, we need to try the other kind of the geometries. So for example, some interferometers, some Josephson junction device, and we may demonstrate this kind of the Marana physics. And one thing I want to point out is in our experiment, we only exclude the observation of the E square over 2H, this kind of plateau in the millimeter size quantum anomaly, millimeter in all this kind of device here is millimeter, is in our maybe 100 micrometers in this kind of the device is not related to the chiral-Marana. We don't quite know when this kind of the device become very small. For example, in nanometer device, in tens of nanometer device, it may using this kind of the geometry to demonstrate the Marana physics in quantum anomalous Hall and the superconductor hybrid structures.
Okay, great, thanks. I have the second question, if I may. The second question is, you mentioned this topological magnetic electro effect, right? So this is to apply some electric field and to observe this magnetic field, if I'm correct, right? So then how do you quantitatively measure this magnetic moment in this case?
Yes, this is actually a very good question. You know, the using a simple words to describe the TME effect is just the, as I show you here, is the induced B, the induced E and applied B parallel with each other. At the same time, the coefficient is quantized. But we know that this kind of the induced B or induced E, this is the when you apply E, it will induce B. When you apply the B, it will induce E. All this kind of the signal is quite very small. And until now, there are several experiments already using the Kerr effect, the optical method, to demonstrate this kind of the GME effect. I think the physics is quite similar, but in the transport, for example, if you want to detect the current signal or electrical field signal or magnetic field signal, all this signal is very small. It's very difficult to quantitatively to demonstrate this kind of the quantized relationship between the M and E.
Okay. Thanks.
Using the optical method already, some I think 2 or 3 group already claimed this kind of they call it quantized optical effect in the magnetic TF film. Different name, but I think the underlying physics should be the same.
I see. Okay, thank you.
Okay, thank you. Other questions? So I have a question also. I mean, for the axion type, I mean, the axion is usually determined by a parameter theta, the coupling of axion. I mean, is yes, this theta. So I mean, is there any way to measure this term here?
Yeah. This theta is related to the, it's just the we usually call a theta term in this here. So for the topological material, theta is 1. We also call it pi. The same. It just depends on different unit you use. And in the normal insulators, the theta is equals 0. So that's the in this kind of structure, if there is the normal insulator, theta is 0, and in topological material, theta is 1. In this kind of the when you change it from normal insulator to topological insulator, it should be a random value between 1 and 0.
Okay, so any other questions? So I have another question also for this multi Chern number system. You go to C to 5, up to 5. I mean, is there any limit somehow? I mean, so at some point there is some kind of finite some size effect that will prevent to go further than that, or in practical, there is no limit in order to increase. So you can increase, if you increase layer by layer, you will definitely do that, or there is some kind of
this is a growth question, actually a very good question. We know that actually, there is a very famous theoretical prediction. If we further increase the, for example, the here, let's see here, is the magnetic tier and the tier bilayer structure, further increase the periods. When the chain number is above some critical value, for example, we call it C0, and we above the C0 is usually can realize, according to the theoretical prediction, you should realize the well-symmetric metal phase. This well-symmetric metal phase is a very unique well-symmetric metal phase. Actually, compared to the natural well-symmetric metal, here is there only a pair of well node here. And this well node actually can be tuned by the magnetization in the film. When you change the magnetization, the well node will sweep each other. So now, and as you said, and now, when we publish this paper, my student further optimized the growth condition. Now I can tell you is the maximum chain number in my group we could grow is the C equal to 10. And when you C equal to 10, actually the whole resistance is quite small. It's just 2.5 ohm. It's very difficult to distinguish this is C equal to 10 or C equal to 11 or C equal to 9. And if you take a careful look here, you can see that when you increase the chain number here, the longitudinal resistance actually goes higher. In my opinion, there are two possibilities. One is just because of the intrinsic property. You know, there are side surface effect. You know, the side surface affects this kind of the finite longitudinal resistance here. And there is another possibility. It's just the growth problem. You know, when you grow the very thin topological insulator film or magnetic topological insulator film, you know, it's very difficult to avoid this kind of the introduction of the impurity or defects in this kind of the growth. So that's the reason. I think here you can see that when the chain number equals to 4 and chain number equal to 5, this is higher. So I think that can be improved by just optimize the growth condition. We may realize the quantum anomalous Hall insulators with the chain number higher than 10 or higher than 5.
I see.
Yeah.
Okay. Okay, so if there is no more questions, I think let's thank you again, Cui-Zu, for this very nice talk, very nice talk, and have a nice evening. And then hope to see you also in Singapore, maybe soon.
Yeah, thank you all. Yeah.
Thank you. Goodbye.
Yeah, bye. Bye.
Bye-bye.